Hi everyone, and welcome to this new video about steady-state analysis. We begin with our design example number 2 about RLC circuit design. We have the following circuit given with a voltage source V in series with the inductor, resistor R1 and the resistor R2. So we have two resistors and one inductor. And the following situation is given for this circuit. Design this circuit to produce the output voltage V out, which is 2 cosine 10,000 pi t minus 40 degrees in volts, when the input voltage is 20 cosine 10,000 pi t in volts. So the frequency is exactly the same again. So for steady state analysis, that is required for specific one frequency. And we would like to, of course, know, because it is a design, we would like to know what are the component values R1, R2, and the inductor value L. So what we do is we start actually with setting up the transfer function. From the transfer function, we will determine the phase and the gain expressions, and it will allow us to determine the component values. So let's first determine the transfer function. So what do we do with the transfer function? What is actually a transfer function? Transfer function means actually you have a transfer from the input to the output. It will have our ratio of output divided by input, and that will give us a lot of information about how the circuit behaves and what kind of response it gives. So that will be V out divided by V in, all in Laplace parameters. And if I want the fraction here, so just the ratio, I would like the V out divided by V in. I don't need the specific values or expression for V out and also the specific expression for V in. That's not really necessary, just the ratio. That means actually I can use the voltage divider rule here. So I can say V out is just actually the resistor or the impedance, it doesn't matter what it is. So in this case, it's just pure resistor. So R2 divided by the impedance seen by the input voltage, which is just actually the complete set in series. So it's actually the following. I have R2 divided by R1 plus R2, all in series, plus the Laplace parameter used for the reactance of the inductor, which is SL. Now, if I now convert this using the situation of S is equal to J omega, which can be used in steady state analysis, I have an expression for the transfer function in J omega domain, which is H J omega is equal to R2 divided by R1 plus R2 plus J omega L. So where you see S, you substitute that by J omega, that's all. Okay, we know from this expression we can get our expression for gain and also the expression for phase. But before I start with the formulas for the gain and the phase, I would like to know what kind of information I get from the data here. So we have the following: at omega specific frequency of 10,000 pi radians per second, I have a gain of, as you can see, we have a 2 volts at the output with an input voltage of 20. That will, of course, 2 divided by 20, it will be 1 over 10, so 0.1. And for phase, at the output I have a minus 40 degrees, and for input I have 0 degrees. So that means actually minus 40 degrees minus 0 degrees will be, of course, just minus 40 degrees. So I have now two situations here. Can be used, of course, this data also will be used in the expressions for the gain and the phase for our expression from the transfer function. What we have is the following: so the gain, and I have also the phase. So I will use these two expressions. So what do I have? I have now an expression for the gain, which is the absolute value of this will be the R2 divided by the square root, so the length of this vector. So that's actually a complex expression. The real part squared plus the imaginary part, which is just omega times L squared. This is actually the gain. For phase, I will use phi omega. That will be, now the phase expression can be determined also from the transfer function. The phase contribution from this minus the phase contribution from the bottom side. So So from the top minus this from the bottom, what you get is actually the following. You have the 0 degrees. Why? Because it's just a real part, so that will be actually 0 phase orientation, so the contribution is 0 degrees. And this one, they will depend on the resistor values and of course on the omega and the L, so that will be arctangent formula. We have dealt with many times in other videos also, so it will be minus because it's this phase minus that phase contribution, so you have 0 degrees minus arctangent of the imaginary part divided by the real part. That's actually now this expression. Now I will now evaluate these two expressions for the gain and also for the phase at specific frequency 10,000 pi radians per second, and I will equate this equal to 0.1 or 1 over 10 and this one to minus 40 degrees, and I will have a set of equations, two of them, and I will use them to calculate R1, R2 and L. So let's substitute the values. So what we have, I will now substitute the omega as 10,000 pi, and I will now equate this to 1 over 10, and I will equate this to minus 40 degrees. What do I see already? I can see the following. I have three unknowns, R1, R2, and the L, which is also valid here. If I now substitute the omega and equate this here to minus 40, and also here omega is 10,000 pi, and equate this to 1 over 10, I still have three unknowns, but I have only two equations. So I have to select one of the components. It doesn't matter what component you select, but you have to select one of the components. It can be a resistor, it can be the inductor, or you can take this resistor or that resistor, that doesn't matter, but you have to select one of them because we have two equations with three unknowns. So we cannot make a unique set of parameters. So I will also select, in this case, also select or take the inductor value, in this case just 10 millihenries. You can take another one, doesn't matter, it will work. So it will be 10 to the power minus 2 henries. So that's actually for this situation. So what will happen is if I now substitute the omegas and also the chosen value for the inductor, we will have the following situation for the gain and also for the phase. So I will have the following: R2 divided by the square root of R1 plus R2 quantity squared plus now J omega omega is 10,000 pi times 10 to the power minus 2, and it will be squared, and this will be 1 over 10. As you can see, I have only two unknowns here because this is R1 and R2, because the L is substituted here, and also the omega. Now, if I now continue, of course, I can just get rid of this 0 degrees, and this will be, of course, equal to minus 40. So I will have the following: minus arctangent, and it will be 10 to the power 4 pi times 10 to the power minus 2 divided by R1 plus R2. So I have now two equations and two unknowns, and that's actually, you can now solve this uniquely. So you can have the following situation. If I now designate this as equation number 1 and this as equation number 2, I can now use equation number 2 to calculate the summation of the R1 and R2. You can also use this equation, but I think this is a little bit simpler to start with. So if I now use from here, so if I now say just start from here and go 10 to the power 4 pi times 10 to the power minus 2 will give us, of course, 10 to the power 2 pi will be 100 pi. And if I now do times minus 1 left side and right side, and I will take a tangent of the left side and a tangent of the right side, I will have the following. So I will have a couple of steps. It will be 100 pi divided by R1 plus R2 will give me tangent of 40 degrees. That's actually for this situation. Now I have now the situation for R1 and R2 very easily calculated. So the R1 plus R2 will be 100 pi divided by tangent of 40 degrees. If you do the math here, you will get 0.839. very close to that. And if I now also designate this equation number 3, I know the sum, I mean, excuse me, this will be 374, I mean. Okay, so I have now calculated the summation of these two resistors. So R1 plus R2 must be 374 ohms. Okay. Can I use this expression? Yes, I can use equation number 3 and equation number 1, because this is just 374. Substitute in here, I will have R2 only left here. So that's actually the following step. So what I do is the following: substitute equation number 3 in equation number 1. What do I have? I have the following: R2 divided by square root of 374 squared plus, this is 100 pi squared, and that must be equal to 1 over 10. And this is actually very simple to calculate. It's actually 0.1 times this expression. It will give you R2. So the value of R2 is actually very easily calculated here. So that will be, R2 will be given as 49 ohms, very close to 49 ohms. Okay, I'm very close because I already know the value of R2, and I have the value of our expression for the summation of R1 and R2, so that will be the following. Then R1 is 374 minus R2, which is now R1 is 374 minus 49. I have calculated already. That will give us 325 ohms, and that will be actually the last one. So I have now all of the components: R1, R2, and of course the inductor we have chosen as 10 millihenries. That's actually your choice. You can choose again the resistor, and it will be also valid, and you will find another inductor and also another value for the resistor. So this is not a unique solution. Alright, that was our second example about our RLC circuit design. If we now look at the circuit in more detail, what you can see is this is actually a filter. Actually, all of the design examples we have considered so far are in a sense a filter. So we have a filter here. What kind of filter is this actually? You can look at the limits. So if I now have 0 Hertz or DC, the inductor will be behave as a short. So we actually have the signal flowing actually directly to the resistor, and we have just the voltage divider here, R2 divided by the summation R1 plus R2. That's actually the maximum gain which you can get. If you increase the frequency, the reactance of this one, the inductor will increase, so you will actually have more reactance here, so you will lose signal. Actually, what you get here, you can also see from the ratios, will be lower and lower as the frequency increases. You can also see that in the expression for the gain. In the expression for the gain, you can see the omega, if this is 0, you have R2 divided by R1 plus R2. If omega increases, 1, 10, 10,000, 1 million, etc., etc., this term begins to increase, and maybe in a limit it will be infinity. It will become, this whole term will approach 0. So it will be minus infinity dBs, in other ways expressed. So this actually, in this case, will be actually a low-pass filter. So it will pass the low frequencies and it will attenuate the higher frequencies. And you can determine actually also the cutoff frequency, which is not the situation for this example. So we have determined actually the complete set for this design, R1, R2, and the inductor. So this is actually our second example again for our RLC circuit design. We will continue with other situations for RLC, much more complicated situation, and also other topics. So if you want to know more about this, follow this channel, subscribe if you haven't done so, and don't forget to share and like. And I will see you next time, and take care.